Bonjour à tous, mon nom est Nicolas Benoit. I'm co-leader with Josué Jotsi of the project called Ring of Fire, Reconstructing Long-Term Environmental Records to Support Regional Assessment. This project aims to develop approaches, methods, and environmental knowledge to support the regional assessment of the Ring of Fire. Today, I'm updating two activities from this project. The Ring of Fire is a region with large deposits of nickel, copper, zinc, chromium, and platinum group mineral. It is located in one of the world's largest wetland systems sensitive to climate change and anthropogenic stresses. In the absence of a federal provincial agreement, this project was relocated to two similar sites representing the pre- and post-mining context of the Ring of Fire. The pre-mining context focuses on methodologies and tools for assessing the presence and the natural behavior of metals and metalloids, considering baseline conditions, response to climate change, and remote anthropogenic emissions. The post-mining context focuses on the geochemical fate of metals and metalloids from mining activities in different environmental media. This project, we are privileged to have a multidisciplinary team with different expertise from American groups and universities. To meet the project's main objective, three activities was proposed. One in Mineric Lake, representing analog pre-mining context, and two in the Chaudière-Appalaches region, representing the post-mining context of chromite deposits. For the rest of the presentation, I will focus on recent developments in activity 2 and 3, the environmental study of chromite deposits and the analytical development of chromium speciation analysis in water. So far, in the post-mining context, we focus on the presence of metals and metalloids by sampling multiple environmental media. In the previous years, we look at natural environments such as surface water, groundwater, lake sediments, wetlands, and anthropogenic environment like mine tailings and wastework deposits. This year we focus on glacial sediments, mainly till, which are ubiquitous in the region as a natural source of metals and metalloids. Till's analysis will provide knowledge on the geochemical background of post-mining context. In the till study, we look at three things: the till characterization, the mapping of heavy mineral dispersal in the glacial sediment, and the identification of potential sources of chromium and other metals and metalloids. Before going out into the field, we first collected and synthesized existing data. Based on this data, we planned an optimal field campaign to cover the region of interest. The field work was carried out by 4 students supervised by Professor Olivier Caron from Université du Québec à Montréal. Sampling was carried out mainly along roadsides and riverbank and took place over 4 weeks in July and August of this year. Samples were collected in the Lac Saint-François watershed. The road network provides good regional coverage as shown by the location of the sample sites on the map here. More than 112 sites were observed, characterized, and sampled. 10 soil profiles were made to characterize the vertical evolution of the geochemistry. To our knowledge, no such profiles exist in the ultramafic context of the region. All samples collected are currently being processed at the UQAM laboratory to meet the requirements of the various analyses. The sample preparation involves sieving the material, analyzing particle size, and preparing fractions required by the analysis methods. A first series of samples will be very soon submitted to the ACLabs laboratory for INA analysis for minor trace elements in low concentrations. To cover all elements of interest, a second series of samples will be submitted to the INRS laboratory for ICP AES and ICP MS analysis for major and trace elements. Then a dozen of samples will be selected for mineralogical identification by TIMA analysis. In addition, we will take advantage of the subactivity to update the superficial geology map of the study area. For now, a high-resolution DEM has been generated from a new LIDAR coverage, and a high-resolution hillshake was also generated based on topographical variations using PCA analysis. These images, supplemented by ground observations, are used to map superficial formation with greater precision. At the end, the revised superficial geology map should provide more precision of contacts between the different units. Now I'd like to turn to the activity based on the analytical development of chromium speciation analysis in water. It is important here to recall the major contribution of the GSC Ottawa laboratory, mainly Paul Gammon and Pierre Pelchat, who made a significant contribution to the methodological development that enabled us to obtain high-quality results. In the next few slides, I will review the main result of the previous work, and based on the interpretation of the recent results, we will illustrate the importance of the chemical context on the separation of the chromium-3 and chromium-6 in water. The results of the previous work show that we have an effective methodology for sampling and analysis chromium-6 in water. The methodology developed have been validated with a commercial laboratory as illustrated by this scatter plot. On the figure, we compare the GSC and the Brooks Applied Labs result for different field protocols. Overall, the graph shows similar results and a strong correlation between the results. We can therefore state that the GSC now has a field sampling and an analysis protocol for chromium-6. At the moment, attempts to improve the analysis are focusing on the ability to report data for low concentration samples. It is important to mention that for now, chromium-3 values can only be reported as a difference between total chromium and chromium-6. Chromium-3 analysis is still problematic. Here's why. The main difficulty with chromium speciation is the chemical context of the sample. To illustrate the importance of the chemical context, we study the stability of the water sample over time by comparing it to two samples, both analyzed shortly after receiving the sample, the blue line on the graph, and then analyzed after 7 months, the orange line. On the first row, the blue circles show that non-preserved samples with low dissolved organic carbon, or DOC, and naturally high pH are stable for chromium-6. The two lines overlap on the graph, but the red circles show a loss of chromium-3 over time. Below, unpreserved samples with high DOC and neutral pH are unstable for chromium-6 and chromium-3, as we can see in the red circle. And moreover, unknown species are generated, as we can see on the blue circle, possibly an amalgam of organic molecules with chromium. Unfortunately, in most environmental media, natural samples have a neutral or slightly acidic pH and are able for chromium speciation, especially at high DOC. Now, preserved samples stored at low DOC and naturally high pH are quite stable for chromium-6, as shown by the blue circles on the first row. Here, the red circle indicates a loss of chromium-3 over the time. reserve samples stored at IDOC are unstable for chromium-6, although there is some stability for chromium-3. And here again, we know the presence of unknown species that appear to be unstable and decomposes to give chromium-6. These recent results, the take-home messages are as follows. Chromium-6 is generally stable except in IDOC environment. IDOC samples are problematic for known chromium speciation methods and is therefore an important issue for wetland context of Ring of Fire. Thus, new methods are needed for IDOC samples. We hope that future experiments using reference materials based on humic and fulvic acids will help to solve this issue. If you're interested in learning more about this project, you can scan the diagrams below for previous presentations. Merci.